This is Sachin Fiske from Electrical Engineering Department. Today we are going to start poles and zeros of a transfer function. Once the concept of this transfer function is understood, let us now move towards the poles and zeros of a particular transfer function. This transfer function of a system is generally represented as g of s. G of s, or let it be, we can consider this one as h of s also. So this g of s is always equals to v0 of s, that is output of the transfer function, to the vi of s, that is input of the transfer function. Or more generally, we can say that g of s is equals to c of s upon r of s. So moreover, we can consider this g of s will be as h of s, and c of s is equals to n of s and r of s, that is d of s, to understood very simply, where this n of s is nothing but the Laplace transform of the output and d of s is the Laplace transform of the output. Now this n of s and d of s are the polynomials in s form. Let us consider one example, that is h of s is equals to bm into s to the power m plus bm minus 1 into s to the power m minus 1, and so on in numerator, and in denominator an, n means in suffix n, an into s to the power n plus an minus 1 into s to the power n minus 1, and so on. It is often convenient to factor the polynomial in numerator and denominator and to write the transfer function in terms of those factors. So let us consider this h of s is equals to n into s, n of s upon d of s is equals to k, and same as it is above, means factorize the above equation. Moving towards the poles and zeros of a transfer function. These poles of a transfer function are the values of the Laplace transform variable s that causes the transfer function to become infinite. See this equation number 1, where s is equals to a1, s is equals to a2, s is equals to a3, and so on, s is equals to an. Here, this transfer function h of s becomes infinite, and hence a1, a2, a3, and an are the poles of the transfer function. If we equate the denominator of the transfer function to 0, then we obtain the poles of the system. Similarly, the zeros of a transfer function are the values of the Laplace transform variable s that causes the transfer function to become 0. Again, we consider this equation number 1, when s is equals to b1, s is equals to b2, s is equals to b3, and s is equals to bm. So the transfer function h of s becomes equals to 0, and hence b1, b2, b3, and bm are the zeros of a transfer function. Now, if we equate the numerator of the transfer function or the polynomial equation of a transfer function, numerator side, we obtain the zeros of the system. As we know that the S-planes, that is Laplace plane, basically consist of an imaginary axis, that is j omega, and the real axis, that is sigma, means S is equals to sigma plus j omega. In the very first line, it is shown. So poles are represented by cross sign, and zeros are represented as a 0 on S plane. Hope everyone got this. In a simple word, we can say that if we equate the denominator of a transfer function equals to 0, then we obtain the value of s, and that values are known as the poles of the transfer function. Similarly, if we equate the numerator of the transfer function equals to 0, then we obtain the zeros of the transfer function, and that is known as the zeros of a particular transfer function. In this way, we can easily find out the poles and zeros of the transfer function. Now, we are moving towards the examples based on transfer function. So, we consider one equation, that is a linear system is described by the differential equation, and this differential equation is noted as d square y upon dt square plus 5 dy by dt plus 6y is equals to 2 dy by dt plus 1. Here it is the second order derivative on LHS side and first order derivative on RHS side. Now we have to find out the poles and zeros of this equation. So before moving towards the poles and zeros of the equation, first we have to convert the given equation in S domain form or in the form of factorization. So basically from this differential equation of the transfer function, let us consider this h of s is equals to, now see on the LHS side, LHS side represents the denominator of the transfer function and RHS side represents the numerator of the transfer function. See here 2 dy by dt means 2 into s. Dy by dt is the first order derivative and therefore it is considered only s. And 1 is only a coefficient. There is no term of dy by dt. So it is 2s plus 1 in numerator. Now what is in denominator? Yes, there is second order derivative and means it is the s square, but there is the absence of any s term. Sorry, there is absence of any coefficient. So it is s square plus coefficient is 5 means s square plus 5s plus 6y only there means y is considered as 1. So 6 into 1 that is 6. So in denominator we can write s square plus 5s plus 6. Now it is in the form of factorization, which may be written in the factorized form as h of s is equals to 2s plus 1 upon s square plus 5s plus 6. Now here in numerator it is 2s plus 1. So instead of 2 we have to make this s having the coefficient 1. So divide it by 2. Each and every term of the equation is divided by 2. Okay, so 1 by 2 is equals to, in numerator we can write 2s plus 1 as s plus 1 by 2, and in denominator also we can write s minus 3 into another bracket s minus 2. Okay, so the system therefore has a single real pole at s is equals to minus 1 by 2, s is equals to, and a pair of real pole at s is equals to minus 3 and s is equals to minus 2. Let us consider one more example, that is a system has a pair of complex consecutive poles p1 p2 is equals to minus 1 plus minus j2, a single zero, that is z1 is equals to minus 4 and a gain factor of k is equals to 3. Now find the real differential equation representing the system, that is the transfer function is given by h of s is equals to k. Now we have a single zero, that is z1 is equals to minus 4. So write down the equation in numerator, that is s minus z, s minus zeros, because this z indicates the zeros of the transfer function, and when we are putting this value of z we get the value of numerator. Similarly, if we put the value of p1 and p2 in denominator, then we get the denominator of a transfer function. So and k obtained as a constant, that is all these values are given. So k is equals to 3, s minus, what is the value of this z? Yes, it is minus 4. So put down all the values like this. So what is the value of p1? Yes, it is minus 1 plus j2 and minus 1 minus j2. All whenever all these values are put in the equation of h of s, we get H of s is equals to 3 into s plus 4 minus minus get plus, so s square plus 2s plus 5 in the denominator, and the differential equation as per the equation number 7 become, here s square plus 2s means there is no coefficient for s square and it is second order, so it is d square y upon dt square plus 2 into dy by dt plus 5 as it is, means 5y is equals to 3 into dy by dt plus 12, 3 4 the 12, so 12 u, and this is basically the solution. Now as per our poles and zeros of the given equation, we can plot these poles and zeros of a transfer function in this way. Thank you.